Hello and welcome. My name is Mario Torres Rodrigo and I'm the applications leader at H.E.L. And today we're going to be talking about the basics of calorimetry. So the first thing that we need to ask ourselves, what is calorimetry? Well, calorimetry can mean a number of things, and the definition is going to change slightly depending on the field of study. But for the purpose of this talk, we're going to focus on a chemical perspective. So in chemistry, calorimetry is the process of measuring the amount of heat released or absorbed during a chemical reaction. So let's just imagine that we have quite a simple reaction in which A is going to react with B to generate a compound C. And energy can behave in one of two ways. It can be the case that for A and B to react, it needs to have energy supplied. So A and B are going to be withdrawing energy from the surroundings as the chemical reaction progresses. And this is what is called an endothermic reaction. On the other hand, it can be the case that A and B, when they react, they're going to be generating energy. And this energy is going to be transferred to the surroundings in what we call an exothermic reaction. And this is the type of chemical reaction we're going to be focusing on, because it can have some risks associated with it. So let's assume that we have small amounts of A and B in the order of milligrams or grams, like the kind of example that you would have in a lab. And we're going to have an open vessel that is going to be on top of a bench. As A and B are reacting, there's going to be an accumulation of heat and compound C and potentially gases as well. But because of the small volumes, the heat is going to be just transferred to the surroundings and the gas is going to escape, and nothing major is likely to happen. This situation is going to change if we have industrial scale experiments in which we're not going to use milligrams or grams, we're going to use kilos and kilos of compound A and B. And instead of using an open vessel, we are likely to use sealed vessels. So we're going to have A and B that they are going to be reacting with each other to generate C, and heat and gases are going to be produced. If we have very high heat accumulation, it can be the case that we have fire risks. And if we have an overpressuring of the system because of the accumulation of gas, it can result in the explosion of the vessel, which can be very dangerous. And this is only if we analyze the desired reaction. So if we think of our reaction A plus B to generate C, and we look at the evolution of the temperature, we can see that it's going to slowly and steadily going to increase until the reaction accelerates, and then we're going to see a spike in the temperature. And the same is going to happen with the pressure. Pressure is going to remain more or less stable until the reaction is going to accelerate, and then we're going to see the accumulation of pressure. And as I said, this is only on the desired reaction, but also there is a whole family of other potential reactions that can happen alongside with our desired reaction. And this is what we call secondary reactions. And among this kind of reaction, thermal decomposition is particularly relevant because they can be quite dangerous. And thermal decomposition happens when a compound breaks into two or more substances, and this kind of reaction can be accelerated by heating. So let's go back to our example, and we have compound C, and it's going to break down into compound A and compound B. It can be the case, if it's an exothermic reaction, that heat is going to be accumulated as well. So if we study how our reaction would progress, we would see that the temperature increases, then it's going to reach a plateau because of the cooling. But if the cooling fails, then we're going to see a sudden increase again on the temperature, and potentially, if our decomposition reaction happens, we're going to see a further increase in this temperature. And to predict this, the onset temperature is a very important parameter, and the onset temperature is going to be the temperature at which our decomposition reaction is going to accelerate, and we are going to be able to detect it. And also we need to wonder, and we need to investigate if our decomposition reaction is going to add heat to the system, even worsening our situation. So understanding chemical reactions is something that we can use with calorimetry, and it can teach us so much about risks. And then knowing these risks, we can add safety nets around the chemical reaction. And a very important parameter in the safety of our reactions is the maximum temperature of synthesis reaction, MTSR. And it is quite an easy value to calculate, and it's just going to be the temperature of a process plus the adiabatic temperature rise. And the adiabatic temperature rise is defined as the temperature change that is going to happen when there is no gain or loss of heat to the environment. So it's just going to be linked to our reaction heat. So thankfully we can also calculate this value, and this is why calorimeters are so important, because thanks to them we can calculate the energy released by the reaction, Qx, but also the thermal mass of the reactants, MCP. That's going to be the mass of the reactants times the specific heat of the compounds that we're going to be analyzing. So if we have an experiment, let's imagine this, in which we're going to have a reactor. This is going to be the cylinder that we can see in the slide, and this cylinder is going to be filled with compound B. Then we can add compound A at a steady rate in order to make the reaction happen. So if we look at the graph we have on the right hand side, we are going to see that the feed is going to be the gray line, and at some point we are going to stop the feed, in this case at 80 minutes. And we can see that the blue line, which is the energy accumulated in the reactor, is going to carry on accumulating even though we stop the feed. And it's going to carry on accumulating until 350 minutes. So this energy release is going to be very important because it's going to determine what our Qx is and what our adiabatic temperature rise is going to be, and we can calculate it as we can see on this other slide. So we have the measuring of heat that we had when we stopped the feed, and then we can calculate the difference between this value and the maximum value of the accumulated heat. And in this experiment, that is going to be 34.6 kilojoules of energy. And we know because of calorimetry that also our reactant's thermal mass is going to be 326 joules per centigrade. The adiabatic temperature is going to be then 34.6 times 1000 divided by 326, and it's going to be 106 degrees. Then if we add that to the 30 degrees, which is the temperature of our reactor, we're going to have a total accumulation of 136 degrees Celsius. So with this kind of information, then we can work towards fabricating and elaborating safer processes. So in this case, knowledge really is power. So we have characterized our chemical reaction, and we have identified the risks and hazards, and now what we can do is putting measures in place to avoid those hazards. So for example, if we know that the onset temperature for the secondary reaction it is lower than the MTSR, then we want to consider to cool down our system so we never reach to that temperature and then we have a thermal runaway. Also, it can be the case that we thought that maybe we wanted to add all our reactants into the reactor, and then we observed that no, that's going to generate a huge MTSR. So maybe we want to move from a batch kind of approach to a semi-batch approach in which we're going to slowly feed one of the compounds into the reactor. But it can also be the case that even using this kind of approach, there's going to be too much accumulation of heat, and then what we can do is playing around with the feed rate. And this is what we're going to see on the next slide, in which the pink line is example that we had before, and we observed that in order to keep our reactor at a temperature of 30 degrees, actually we need to supply 15 watts of cooling. And this was when we were supplying 2 grams per minute. And then we can think maybe that kind of cooling is too much for us, we can't cope with it, so let's see what happens if we reduce the feed rate, and instead of using 2 grams, we're going to use 1 gram, and that's going to be the blue line. And actually, we see that we don't need to supply as much heat, as much cooling, and instead of 15 watts, it's going to be just 8 watts. So actually, calorimetry can teach us how to calculate how to address these issues. So before we leave, I just want some messages for you to take home. The first one is that calorimetry studies the exchange of heat, and exothermic reactions, both desired and secondary, can result in risks. However, nothing is a loss, because actually lessons learned from calorimetry can help us to design safer reactions. And that's pretty much all from me. As I said at the beginning, my name is Dr. Mario Torres Rodrigo, and I work for H.E.L. And if you want to reach out, if you have suggestions, if you have comments, please just come and talk to us. Thank you very much.